Welcome to the channel Physicscompanion. In this video, let us try to understand two important concepts: specific heat capacity and latent heat. Now let us consider, for example, 1 liter of water, and I just considered in a vessel, and I am now supplying an amount of heat Q to raise it by 20 degrees centigrade. Let's say. Then I use a stop clock and measure the time taken. Let's say it has t seconds taken. Now I repeat the same thing by raising it to 40 degrees centigrade. Then, as you know, the time taken is twice the time taken to raise it to 20 degrees centigrade with the same amount of heat supplied. Which means you need to double the rise in temperature, you need 2Q, that is twice the heat, to raise it in the same time, in same t seconds. Let us say now I double the water, so 2 liters of water now, and I consider more water, 2 liters of water, and I'll supply the same heating arrangement, and I supply the same heat to raise it to 20 degrees centigrade again. Then the time taken will be 2t, twice the time, because here we have doubled the quantity of water. Now let us say I take same 1 liter of oil now. Instead of water, I'll take oil and I heat with the supply of the quantity of heat to raise it to 20 degrees centigrade. Then it takes less than t seconds, which implies it requires less than the amount of heat Q to be supplied. Now, the quantity of heat Q required in all this observation, the quantity of heat Q required to warm the substance depends on, through this observation we can see that it depends on 3 factors. Number 1, its mass. 2, the change in temperature. And 3, nature of the substance. As you can see, if I consider oil and if I consider water of same quantity rising to the same temperature rise, supplying the taking in the supply, then it takes less time and it requires less heat in case of oil, as you can see. So it depends on nature of the substance, the change in temperature and mass. So these are the important. So now let's see the change in temperature of a substance. The change in temperature of a substance when a given quantity when a given quantity of heat Q is absorbed or rejected by it, is characterized by a quantity called the heat capacity of that substance. So what do we understand? The change in temperature of a substance, we have changed it to raise it to 20 degrees centigrade, 40 degrees centigrade, so by supplying the same amount of heat. So when a given quantity of heat Q is absorbed or rejected by it, is characterized by quantity called heat capacity of the substance. Heat capacity of the substance, and is denoted as S, and that is can be written as delta Q by delta T, where delta Q is the heat supplied to the substance to change its temperature to change in temperature from T to T plus delta T. Then the change in temperature will be delta T. So this is the heat capacity of the whole substance. Now let us define what is specific heat capacity. This is very important, specific heat capacity, and I'll denote it with a letter small s. It is the heat delta Q, it is the heat delta Q absorbed or rejected to change the temperature of unit mass out of the whole substance, unit mass of the substance by 1 unit. So out of the whole substance, specifically for a unit mass, when you are measuring the heat capacity, then it is called specific heat capacity. So this S now can be written as 1 by m delta Q by delta T, and the SI unit for this is for Q, that is heat, joules, and mass kg inverse, and temperature Kelvin inverse. So it is a property of the substance which determines the change in temperature of the substance without change in phase. That means there is no change in phase, without phase change. So that is important here. That means there is a change in temperature with respect to specific heat capacity without phase change. Now if I am considering, so now let us talk about molar specific heat capacity. Specific heat capacity, molar specific heat capacity, and I denote this with a letter C. Now what is molar specific heat capacity? Instead of unit mass, we will now consider 1 mole of a substance. 1 mole of a substance. So molar heat capacity C, now we will write 1 by mu delta Q by delta T. So that is S by mu. Here it is capital S by M. S by mu, where mu is number of moles of the substance. number of moles of the substance, that is per mole of a substance. Now specifically, if we are talking about if the substance is a gas, so for gases you have at constant pressure, you can write Cp, at constant volume, specific molar specific heat capacity, Cv. So the suffixes P and V refer at constant pressure and volume for the substance if the substance is a gas. Then you will call this as molar specific heat capacity of a gas at constant pressure, this as molar specific heat capacity of a gas at constant volume. Water has the highest specific heat capacity, and that is why compared to other substances. So that is why it is actually used as a coolant in radiators, automobile radiators. So as a coolant in automobile radiators, as well as heaters in hot water bags, because of having highest specific heat capacity for water. Now let us define what is calorimetry. It is a branch of physics which deals with the heat transfer. It deals with the heat transfer and measurement of heat. We said there is some heat supplied or rejected, Q. So we will measure that heat, measurement of heat Q. How much amount of heat Q is either supplied or rejected can be measured, and it is measured in calories or kilocalories, in calories or kilocalories. A device used to measure heat. So a device based on this principle used to measure heat is called calorimeter. Calorimeter, which is used to measure specific heat of a substance, usually which can be used to measure specific heat of a substance. So what is the principle here? So principle of calorimetry. So when you have two bodies, either solid or liquid or both liquids at different temperatures, let's say T1 and T2, and both are in thermal contact, then heat will be transferred from a body at higher temperature. Let's say T1 is greater than T2 here, so heat will be transferred from a body at a higher temperature. I call this as hot body and I call this as cold body, lesser temperature. So heat from the hot body to cold body or higher temperature to lower temperature, lower T, higher T, till when this transfer will take place, until these two will attain an equilibrium temperature. Further, so they attain equilibrium temperature provided no heat is allowed to escape through the surroundings. That means there is no other heat loss. No other heat loss to the surroundings within this experimental setup. So the body at higher temperature releases heat. Hot body releases heat Q, and cold body absorbs. Cold body at lower temperature absorbs it. So heat lost by the hot body is equal to heat gained by the cold body. So this is the principle. So I repeat, when two bodies at different temperatures are brought in contact, heat will be transferred from the body at higher temperature, that is hot body, to the body at a lower temperature, that is cold body, until when this transfer of heat will take place, until both acquire a same temperature. So I call this as equilibrium temperature, or we can call them as thermal equilibrium, provided there is no heat is allowed to escape through the surroundings. So there is no heat loss otherwise. Then this hot body releases the heat during this process and the cold body absorbs heat. Therefore, heat lost by the hot body is equal to heat gained by the cold body, which actually represents the conservation of energy. Conservation of energy. Now, how do we define then a calorie, the unit? It is defined as the amount of heat required to raise the temperature of 1 gram of water through 1 degree centigrade. So this is what we define a calorie. The amount of heat required to raise the temperature of 1 gram of water through 1 degree centigrade. Now let us try to understand mechanical equivalent of heat J. So according to Joule, work may be converted to heat, or work W can be converted to heat Q, or vice versa. So the ratio of work done to heat produced, that is W by Q, is constant. This constant is called mechanical equivalent of heat. This constant is called mechanical equivalent of heat J, which is equal to 4.18 joules per calorie. Now to understand this, now let us say there are two bodies, hot body and cold body, A and B, of masses M1 and M2 at temperatures T1 and T2. So this is hot body, this is cold body. This we also call as method of mixtures. Cold body. And let the equilibrium temperature be T and their specific heats be C1 and C2. C1 and C2. Then heat lost by hot body A is equal to heat gained by cold body B. So, from the formula that we have discussed, specific heat capacity is 1 by m delta Q by delta T. Either if it is for mole, mu, otherwise then. So, let us say I will write small s, or C is 1 by mu delta Q by delta T, whatever it is. Then, so Q is equal to m s delta T or mu C delta T. So, I will consider this for the simplicity. So, I will write m1 C1 T1 minus T for the hot body, T1 minus T, that is delta T for the hot body, and I will write this as m2 C2 T minus T2, that is the change in temperature. So, this is the change in temperature and this is the change in temperature. So, that gives you delta T. So, m S delta T. So, here I am considering C. So, m1 C1 delta T, m2 C2 delta T. So, delta T is T1 minus T here and T minus T2 here. Therefore, that thermal equilibrium temperature T can be written as m1 C1 T1 plus m2 C2 T2 by m1 C1 plus m2 C2. This is an important expression which is used to solve many problems. Now, from this one, let us see if the bodies, different cases, if the bodies are of same material, then C1 is equal to C2. Then we can write T is equal to m1 T1 plus m2 T2 by m1 plus m2. That is case 1. Another case, if the bodies are of same mass, here we have different variables. So, if they are same mass, then I will write m1 is equal to m2. Then T is equal to T1 C1 plus T2 C2 by C1 plus C2. If C1 is equal to C2, M1 is equal to M2, then that means combining both the above conditions, then we have T is equal to T1 plus T2 by 2. T1 plus T2 by 2. So, that will be the average of the two temperatures. The thermal equilibrium temperature will be. Now, let us see thermal capacity. So, these are used for problems. Thermal capacity. Amount of heat required to increase the temperature of a body by unit degree. So, S is equal to dq by dt. dq I will write mc delta t, that is dt by dt. So, that is equal to mc. So, S is equal to mc. Mass into, that is mass into specific heat. Mass into specific heat. So, that is thermal capacity. We will discuss latent heat in my next video. Until then, keep watching, keep learning. Thank you.